Hi everyone, in this video we are going to discuss about how to calculate the sum of interior and exterior angles of any polygon. So we are going to start our discussion with the simplest polygon, which is a triangle. Suppose we have a triangle like this, three vertices are A, B and C, and we have to find out what is the sum of the interior angles. And when I say interior angles, I mean these yellow angles right there. Probably you already know that the sum of interior angles of a triangle is 180 degree, but do you know how to prove it? I mean, where did it come from? So let's quickly take a look at the proof, and then we are going to use this concept, meaning we are going to use this theory that the sum of the interior angles of a triangle is 180 degree, and we will be using this theory to calculate the sum of the interior angles of other types of polygons like quadrilaterals or pentagons or hexagons or heptagons, So for the proof, I'm going to add something extra to this triangle, and let's do that first. Let me first complete the drawing and then we'll discuss. So what I have done here, I have extended the side BC up to D, and also I have drawn a line which is parallel to the side AB. So think about line CE. Let's assume that line CE is parallel to the line AB, and CD is nothing but an extension of the side BC, right? So now let's take a look. Now that we have two parallel lines, if we assume that the side AC is a transversal, then can we say it like this, that because these two lines, meaning AB and EC, they are parallel, and if we assume that the side AC is a transversal, then we can easily say that these two angles are going to be equal. Like now I am highlighting with a pink arc here. So this angle and this angle, they will be equal angle because they are the alternate angles. So I can say, okay, if this is alpha, then this is also going to be alpha. And similarly, between these two parallel lines, if we assume that the side BC is also a transversal, then you can see that this angle right here, now let me draw the angle in green color here, so I'm changing the color to green now. So this angle right here, which is the angle B, it will be equal to this little angle right here, which is the angle ECD, because they will be the corresponding angle. And then the only other remaining angle is this angle, the angle original angle C, which is the angle BCA. That angle is actually a common angle. Now if you think about it, you see this one angle right here, which is a straight angle at point C on the upper side of the line BD. You see the angle that I have drawn with a red arc, that angle is actually a straight angle. And if you think about that angle is actually a sum of three angles there. So can we say that this straight angle right here at the point C on the upper side of the line BD, we have a straight angle, and that straight angle is actually 180 degrees. So let me make a quick note here. So we can say 180 degree, which is the straight angle, that is actually a sum of alpha and beta and the angle ACB. And then what is the sum of the interior angles of this triangle? Well, if you now look at the picture of the triangle here, you see that the sum of the interior angles would also be alpha plus beta plus this angle ACB, and we have already found the value of that. So this is actually the sum of the interior angles. If I highlight it, this is actually the sum of the interior angles of this triangle. The alpha angle, the beta angle and the angle ACB. Those are the three interior angles, and their sum is actually now looking like 180 degree. So now we can also make a quick note here. We can say, okay, so this sum, the sum of the interior angles of this triangle would be 180 degree. I hope it is clear up to this point. And now we are going to use this theory to calculate the sum of the interior angles of other polygons. Now I'm going to draw a couple other polygons and then we'll discuss. Let me first draw them. So here in the diagram, I have drawn two polygons here. One is a quadrilateral and another one is a pentagon. So first we'll be talking about the quadrilateral, and we'll try to calculate the sum of the interior angles of this quadrilateral. Now I'm going to take the point A or the vertex A. So if you think about the vertex A, from here, how many diagonals can we draw? Well, if you think about it, the vertex B is collinear with A, so we cannot really draw any diagonal from A to B. Similarly, the vertex D is also collinear with A, so from A to D there is no diagonal. So the only other vertex, which is the C, that is the only vertex through which we can draw a diagonal from A, right? So let's draw that diagonal. So now looks like our quadrilateral has been divided into two triangles actually, the triangle ABC and the triangle ACD. And now all of the interior angles, let me highlight them, all of these interior angles, you see I am highlighting with a yellow arc. So all of those interior angles of this quadrilateral, their sum will be the sum of the interior angles of these two triangles. If you think about it, so suppose let's call them, let me first highlight the interior angles for the triangle ABC. I am using a pink arc here to indicate the interior angles of the triangle ABC, and then I am going to use a green arc there to indicate the interior angles of the triangle ACD. Now what I am going to do, I am going to give them a certain name here. Say suppose this is lowercase a degree, say suppose this is our A degree, and let's say this is our B degree angle, and then this is our C degree angle, and then let's call this one as maybe D, and then maybe E, and then probably F. So now if we say, okay, so what is the sum of the interior angles of this entire quadrilateral? Well, that would be, if you start with the vertex A, then we can say, okay, that would be A plus E, that is that one angle of the quadrilateral which is actually divided into two pieces, A and E. So you can say, okay, the sum then would be equal to A plus E, these two angles, and then of course plus B, and then of course plus C plus D, and then we are left with the F, so plus F. Now if you think about it, if we sum up all of these angles, whether they are in degree or radian, doesn't really matter. If we add all of these angles, it should give us the sum of the interior angles of this quadrilateral. And now I am going to rearrange this a little bit. Can we write it like this? Can we say, okay, so I am keeping the A plus B plus C together, and then I am going to keep the D plus E plus F together. And now if you think about it, what is A plus B plus C? Well, A plus B plus C is actually the sum of the interior angles of the triangle ABC. So can I replace this with 180 degree? Because we have already proved that the sum of the interior angles of any triangle is 180 degree. So for A plus B plus C, the lowercase a plus B plus C, I am now using 180 degree for that sum of the angles there for the triangle, right? And similarly, we have D plus E plus F, and if you think about it, actually D plus E plus F is the sum of the interior angles of the smaller triangle, which is triangle ACD. So for triangle ACD also, the sum of the interior angles would be 180 degree. So from here, what do we get? We get 2 times of 180 degree, which will be total 360 degree, but I am intentionally writing it like this so that I can show you a nice little concept here. So now if you think about this 2, now what is that 2? Well, 2 is actually the number of triangles that we could create from this quadrilateral, right? And then again, can we write that 2 as 1 plus 1? And now if you think about it, what is that 1? Well, the first one, if you think about this first one right there, the yellow underline first one there, that one is actually telling us that we have so many vertices available to draw diagonals. If you start from any of the vertex, then we are left with only one vertex here for a quadrilateral. I am again going up a little bit here. You can see that if we started with the vertex A, and then B and D, they are actually collinear with A. So we really cannot draw any diagonal from A to B or A to D. So the only other vertex is C, through which we can draw a diagonal from A. So here you can think of this one as the only vertex available to draw a diagonal from A, right? And now I am going to interpret this one as 4 minus 3, and then plus 1 times 180 degree. And now if you are thinking, okay, what is this 4 minus 3? Well, 4 minus 3, I'm writing it like this because then I can say, okay, 4 is the number of sides of this polygon, and then we lose 3 vertices because we are going to draw the diagonals from one of the vertices, right? And then there are 2 other vertices which are collinear with that one vertex. So there are 3 vertices that's not going to give us any diagonal, right? So there will be only one vertex which is going to give us a diagonal in this case, right? Now when you go to a pentagon, the story will change slightly. Actually, the number of vertices will increase a little bit. That would give us a diagonal. But for a quadrilateral, we are actually getting only one vertex through which we can draw a diagonal. And in any polygon, you can always assume that these 3 vertices like the A, B and D, they will not be available to draw any diagonal, so that we can divide the polygon into triangles, right? So how many of our sides we have? We have to subtract 3 vertices because there are 3 vertices which are gone. We really cannot draw any diagonal. And then from the number of sides, if I subtract 3, then I am going to get so many vertices through which I can draw a diagonal. And now anytime I draw a diagonal, I get actually one extra triangle there. Why? Because you see in this picture, I drew only one diagonal and we got two triangles. So if we are able to draw like maybe two diagonals, then we'll get three triangles, which is exactly the case that we'll see in case of a pentagon, right? Now for a quadrilateral, we are able to draw only one diagonal and we are getting two triangles. So that is why I'm saying, first we need to figure out what is the number of sides, and I'm using n to indicate that is the number of sides of this polygon, and then three vertices are not available to draw any diagonal. So n minus 3 would be the number of vertices through which we can draw simple diagonals, and then anytime we draw a diagonal we get one extra triangle. So if I draw one diagonal, I'm going to get two triangles. If I draw two diagonals, I'm going to get three triangles. If I'm able to draw three diagonals, then we're going to get four triangles, and so on, right? So that is how the formula is like this. So multiplied by 180 degree. So now we have a nice little formula that says that, hey, your sum of the interior angles would actually be like this. And if we simplify this a little bit, we can say, okay, so this should be n minus 3 plus 1. So that would be n minus 2. So I'm just simply writing it like this, n minus 2 times 180 degree. So this is the formula for sum of the interior angles of any polygon where the n is the number of sides. So let me make a quick note here that this n right here, this n indicates this n is actually number of sides. I hope the concept is clear. And now let's try the same trick with a pentagon. So I'm now going to scroll up a little bit. So for this pentagon, again, we're going to lose three vertices like the A, B and E. We're going to lose three of them because we really cannot draw any diagonal from A to B or A to E. So now out of the five vertices, because it is a pentagon, it will have five vertices. And out of the five vertices, how many vertices we are going to be left with? Well, we're going to be left with two vertices, right? Which are the C and the D. So from A, we can draw two simple diagonals from A to C and A to D. So let me draw the diagonals. So now you see that we have drawn two diagonals from A to C and A to D. And here, because we have drawn two diagonals, we are getting three triangles inside. You see, when for a quadrilateral, when we were able to draw only one diagonal, we got two triangles. Here we drew two diagonals and we are getting three triangles. And similarly, when you go to hexagon, you will be able to draw three diagonals and you will be getting four triangles. So for a pentagon, clearly we are getting three triangles here, right? And now let's again do the same exercise. Here the sum of the internal angles would be, then let me write it down like this. Suppose let's give a name to each of these angles right here. So suppose this angle right here, let's call it lowercase a. Then this angle right here, we're going to call it lowercase b. And then one up here, that would be lowercase c. And then this one, that would be lowercase d. And then we can call this one as lowercase e. And then the angle up there, we can call that lowercase f. And then there is one angle right here, that is, we can call it lowercase g. And then this can be named as lowercase h. And this angle can be called lowercase I. Right? So now if I add up all of these little angles, that is actually going to give us the sum of the interior angles of this pentagon, right? So now we can say that, okay, the sum of the interior angles here, so here the sum would be equal to, so now I'm going to write, okay, so this would be A plus B plus C plus D plus E plus F plus G plus H plus I. And then if you think about it, if we group them together like this, suppose we are now going to group them like this. Let's say suppose A plus B plus C together, and then D plus E plus F together, and then G plus H plus I together. And if you think about it, they are actually the sum of the interior angles of these little triangles that we have created. So for example, A plus B plus C would be the sum of the interior angles of the triangle ABC, and also the sum D plus E plus F, that would be the sum of the interior angles of the triangle ACD. And then similarly the sum G plus H plus I, that would be the sum of the interior angles of the little triangle ADE. JEE, right? That means each of these little sums here, each of these groups here within the parenthesis, each of these groups will be equal to 180 degrees. So we are going to get 3 of the 180 degrees. So the first group, which is A plus B plus C, that is going to give us 180 degrees. So let me make a note here. And then the second group will also give us another 180 degree, because that is also sum of the interior angles of another triangle. And then the third group will also give us another 180 degree. So that's all we are getting, right? Now I'm going to write it slightly differently. So we can say, okay, now this can also be written as 3 times 180 degree. And then this 3, can we say it, okay, can we write it as 2 plus 1 times 180 degree? And then can we write this 2 as, now I am going to write this 2 as 5 minus 3. Now if you are thinking, hey, what is this 5 and 3? I'll explain. It's similar to exactly what you saw for the quadrilateral, that it is exactly like this. So this 5 is actually the number of sides. This is the number of sides, and then we lose 3 vertices. In this particular picture, we are losing the B and the E and A. So A, B, E, those are the 3 vertices that we lose. We cannot draw any diagonal. And then because it is a pentagon, we are left with 5 minus 3. So we are left with 5 minus 3 number of vertices through which we can draw simple diagonals. And because for every diagonal we get one extra triangle, so if we draw 5 minus 3 number of diagonals, we are going to get 5 minus 3 plus 1 number of triangles. So that is why here we are actually getting 3 triangles, because it's a pentagon. So it would be 5 minus 3. That will be the available vertices through which we can draw diagonal. And because we are able to draw so many diagonals, we are going to get one extra triangle. And that is why I have it as 5 minus 3 plus 1 times 180 degrees. So then we easily convert this into a formula. We can say, okay, this is going to be then n minus 3. N is the number of sides of the polygon, and then plus 1 times 180 degree. And then if we simplify this little bit, this is going to look like this. We can say, okay, n minus 3 plus 1, so that is actually n minus 2 ultimately, times 180 degree. So here also you can see that the sum of the interior angles of pentagon also looking like exactly same as the one we got for quadrilateral. It's always n minus 2 times 180 degree. So you can try the same thing for a hexagon or heptagon, octagon, nonagon, decagon. You will get the same formula. So ultimately for any polygon, you will see that the sum of the interior angles are becoming n minus 2 times 180 degree, where n is the number of sides of that polygon. And one thing you should also understand, that how many ever sides we have of a polygon, we have so many vertices also. So if it is a quadrilateral, there are 4 sides and there are 4 vertices. If it is a pentagon, there are 5 sides and there are 5 vertices. So number of sides and the number of vertices are always equal for any polygon. I hope everything made sense so far. And now let's talk about the sum of exterior angles. So now if we think about exterior angles, what is an exterior angle? Let me draw a quick little diagram here and I'll show you what an exterior angle is. Now if you think about this little triangle here, triangle ABC, I have indicated the interior angles with a yellow arc, and what I have done, I have extended each of the sides little bit with the green dotted line, and I have denoted the exterior angles with a pink arc. So an exterior angle is actually the supplementary angle of the interior angle. So it would be 180 degree minus the interior angle, right? So now if you think about it, what would be the sum of the exterior angles? Well, let's give them a name. Say suppose this angle right here is suppose lowercase a right here. So I'm going to say, okay, this is our lowercase a, and then this is lowercase b, and this is lowercase c. And then let's also give a name to the interior angles. Let's say suppose this is alpha and this is beta, and let's say this is gamma, alpha, beta, gamma. We can name it like that. So now if you think about it, we can say, okay, then a plus alpha. So I'm just writing like this, a plus alpha is equal to 180 degree, because that would be a straight angle. And similarly, b plus beta, that is also going to be 180 degree, and c plus gamma, that is also 180 degree, because each of them would be a straight angle there. So now if you add them, we're going to get a plus alpha plus b plus beta plus c plus gamma is equal to, so then this will be equal to 180 degree plus 180 degree plus 180 degree, which should be 540 degree, but I'm intentionally writing it like this so that we can easily show something right here. So from here we can say, okay, can we write them like this? Can we say, okay, how about a plus, I'm just grouping the a plus b plus c. I'm grouping the a, b and c together. Then plus we have the alpha plus beta plus gamma, and all of that is actually 3 times of 180 degree. Right, and from here you can see that a plus b plus c, that is actually the sum of the exterior angles. So in place of a plus b plus c right here, I'm now going to say this is our sum. So we can say, okay, the sum is now, okay, the sum plus, what is alpha plus beta plus gamma? Well, alpha plus beta plus gamma is actually sum of the interior angles of this triangle, and that would be 180 degree. So that would be 180 degree, and all of that is equal to 3 times 180 degree. And then from here we can do a quick little math right here. So we can say that the sum of these exterior angles, so this sum is nothing but the sum of the exterior angles, would be equal to 3 times 180 degree minus 180 degree, and that would be equal to 2 times 180 degree, and you can also write it as 2 times pi radian, because 1 pi radian would be 180 degrees, so you can say it as 2 pi also, right? If you say degree, it would be 360 degree obviously, or if you want to say in terms of radian, then it would be 2 pi. So 360 degree or 2 pi. Now let's do the same exercise for a quadrilateral also. So let me first draw the quadrilateral. So here I have a quadrilateral where the vertices are A, B, C and D, the uppercase A, B, C, D. That's a quadrilateral, and the interior angles have been denoted with a yellow arc, and their magnitude or their value or the size of the angles has been denoted with lowercase letters like E, F, G and H. And also I have drawn, or I have extended each of the sides to show you the exterior angles. So we have the exterior angles B, lowercase b, and then the other exterior angle would be lowercase c, and then lowercase d and the lowercase a. So we have A, B, C, D, those are the 4 exterior angles. Now we want to find out what is the sum of those exterior angles, right? So now if you think about it, if the exterior angles are always like this, they are actually the supplementary part of each of the interior angles. So an exterior angle again is the supplementary angle of each of the interior angles. So now here, can we write it like this? Can we say, okay, if we say lowercase a plus lowercase e, so if we say lowercase a plus lowercase e, that would be 180 degree, because that would form a straight angle there. And similarly, if we say lowercase b and lowercase f, so if you say b plus f, that is also going to give us another 180 degree, because that will also form a straight angle. And similarly, c plus g will be 180 degree, and also d plus h, that will also give us 180 degree. So now if we add all of them together, they're going to kind of look like this. So I'm now going to write it here. So you can say, okay, a plus e plus b plus f plus c plus g plus d plus h, all of that would be equal to 4 times 180 degree, right? And from here I'm going to rearrange little bit. I'm going to say, okay, let's now write it like this. Let's say a plus b plus c plus d, and let's group them together, because this is actually going to be the sum of the exterior angles. And then what is left? Well, we are left with e plus f plus g plus h, and all of that is equal to 4 times 180 degree. And from here we can say, okay, in place of a plus b plus c plus d, I can say this is the sum of the exterior angles, plus we have e plus f plus g plus h. Well, that is actually the sum of the interior angles of a quadrilateral. So that sum would be n minus 2 times 180 degree, where n is the number of sides of this polygon, and all of that will be equal to 4 times 180 degree. And from here, let's now substitute the value of n also. So we are going to keep the sum. This is the sum of the exterior angles. We can keep it on the left hand side, and then this will be 4 times 180 degree minus, now in place of n, I'm going to use 4, because we are now talking about a quadrilateral. It has 4 sides, right? So n is 4, then minus 2 and times 180 degree. So now this is actually 4 times 180 degree minus 2 times 180 degree, and this is going to give us 2 times 180 degree, which is also 360 degree, or you can also say this is 2 pi radian, right? So now if you see, for a triangle also we got the sum of the exterior angles as 360 degree, and for a quadrilateral also we are getting it as 360 degree. And in fact you can try it for a pentagon or hexagon or heptagon. For any polygon you will ultimately see that the sum of the exterior angles are becoming exactly like this. They are actually like this, 360 degree, right? So that is a constant. So the sum of the exterior angles really does not depend on the shape or the number of sides of a polygon, whether it's a triangle or a quadrilateral or a pentagon or a hexagon or a heptagon, whatever the polygon may be, the sum of the exterior angles, that sum is always a constant, and that is 360 degree or 2 pi. So let me quickly summarize it. So finally we see that the sum of the interior angles of a polygon is equal to n minus 2 times 180 degree, and then sum of the exterior angles of a polygon is always a constant, that is 360 degree. And finally let's talk about the size of each interior and exterior angle of a regular polygon. Now when you say regular polygon, how do we define a regular polygon? Well, if a polygon has all sides of equal length and all of the interior angles are of equal size, then that kind of a polygon will be called a regular polygon. That's just by definition, right? So for example, if you think about a quadrilateral or even a triangle, if you think about a triangle, what would be a regular polygon for triangle? Well, it would be an equilateral triangle. How about a regular quadrilateral? Well, we can say square. And how about a pentagon? Well, we can simply say regular pentagon. And if we want to talk about hexagon, then here also we have to say regular hexagon because there is no other special name. So from pentagon onwards, it will be like regular pentagon, regular hexagon, regular heptagon, regular octagon, and like that, right? So those are the examples of regular polygon. Now we are going to try and find out what would be the size of each interior angle of a regular polygon. Now from our formula up above, we know that the sum of all of the interior angles, that is equal to n minus 2 times 180 degree. So let's use that formula. So what would be the size of each interior angle of a regular polygon? So each interior angle of a regular polygon will be equal to n minus 2 times 180 degree whole divided by n, because we have so many interior angles. If the number of sides is equal to n, then the number of interior angles would also be equal to n. If you think about it, if suppose a triangle, for a triangle number of sides would be 3 and number of interior angles also 3. Even for a quadrilateral, number of sides are 4. Similarly, number of interior angles would also be 4. For a pentagon it would be 5, for a hexagon it would be 6, and so on. So if we don't know what is the number of sides of a polygon, and if we assume that the number of sides is n, then we can say that the size of each interior angle would be equal to the sum divided by n. So we have already derived the formula for the sum, which is n minus 2 times 180 degree, and we are simply dividing it by n. That would give us size of each interior angle. And similarly, what would be the size of each exterior angle? Well, the size of each exterior angle would be equal to, we know that the sum is 2 pi or 360 degree, whatever way you want to say it. I can say, okay, this is 2 pi and we have to divide that by n, because for a regular polygon, the size of each exterior angle will also be equal, meaning all of the exterior angles will be of equal size. And if the polygon has n sides, then obviously there will be n number of exterior angles, and we know that their sum is always 2 pi. So if we divide that by n, we will get the size of each exterior angle, and also we can write it as 360 degree divided by n. I hope everything made sense. Thank you for watching. See you in the next video.